Have you ever looked up at the night sky and wondered, where did it all begin? The vast expanse of space, filled with countless stars and galaxies, sparks a fundamental question within us about our origins. How did this incredible universe, which houses everything we know and love, come to be? It's a question that has captivated humanity for millennia, leading to countless myths and scientific inquiries. Today, the leading scientific explanation for the origin of our universe is a captivating concept known as the Big Bang Theory. The Big Bang Theory is not just a catchy name, it's a profound scientific framework supported by decades of observational evidence and theoretical modeling. It tells a story of an incredibly small, dense point containing all the energy and matter of our universe, exploding outward and evolving over billions of years into the cosmos we observe today. Imagine a time approximately 13.8 billion years ago. Our universe as we know it did not exist. Instead, all of space, time, matter and energy were compressed into an infinitesimally small point, much smaller than even an atom. This point was unbelievably hot and dense, a state physicists call a singularity. Then, something extraordinary happened. This singularity began to expand rapidly in a massive burst of energy and light, an event we now call the Big Bang. This wasn't an explosion in the conventional sense like dynamite going off in a pre-existing space. Instead, it was the expansion of space itself. The Big Bang marked the beginning of space and time as we understand them. From that moment onward, the universe has been continuously expanding and cooling, leading to the formation of stars, galaxies, and eventually, planets like our own. To understand the expansion of the universe, imagine an uninflated balloon. Now imagine drawing tiny dots on the surface of the balloon, each dot representing a galaxy. As you inflate the balloon, observe what happens to the dots. They all move away from each other, just like galaxies in our expanding universe. This simple analogy helps visualize how the fabric of space itself is stretching, carrying galaxies along with it. The further apart these galaxy dots are on the balloon, the faster they appear to move away from each other as the balloon inflates. Similarly, astronomers have observed that the farther a galaxy is from us in the universe, the faster it seems to be receding. This observation, known as Hubble's law, provides compelling evidence for an expanding universe and supports the Big Bang Theory. The first moments after the Big Bang were incredibly dynamic and marked by rapid changes. In an instant, the universe was born from a singularity, a point of infinite density and temperature. This event set the stage for everything that would follow. In the first fraction of a second, known as the Planck epoch, the universe was so hot and dense that our current understanding of physics breaks down. During this time, the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. It's a realm where quantum effects and gravity were equally dominant, a condition physicists are still striving to describe fully. Theories like quantum gravity and string theory aim to explain these extreme conditions, but a complete understanding remains elusive. As the universe cooled slightly, it underwent a period of exponential expansion known as cosmic inflation. This phase lasted for a minuscule fraction of a second but had profound effects on the universe's structure. This rapid expansion stretched the universe to an enormous size in a fraction of a second, smoothing out its initial state and seeding the tiny fluctuations that would later grow into galaxies. These fluctuations were quantum in nature, tiny variations in density that would eventually lead to the large-scale structure of the cosmos. As the universe continued to cool, energy began to condense into matter, forming the first elementary particles like quarks, electrons, and their antiparticles. This process, known as baryogenesis, is still not fully understood but is crucial for the matter-dominated universe we observe today. These particles interacted with each other, eventually giving rise to protons and neutrons, the building blocks of atoms. Through a process called nucleosynthesis, these protons and neutrons combined to form the first atomic nuclei, setting the stage for the formation of atoms and, eventually, the complex structures we see in the universe today. Section 5. Echoes of the Bang Evidence for the Theory. While the Big Bang Theory paints a compelling picture of the universe's origin, it's not just a captivating story, it's backed by strong observational evidence. Scientists have gathered data from various sources that support this theory, making it one of the most robust explanations for the birth of our universe. One of the most compelling pieces of evidence is the cosmic microwave background radiation, or CMB. This radiation is a critical piece of the puzzle, offering a glimpse into the universe's infancy. The CMB is the faint afterglow of the Big Bang, a faint whisper of light and energy that permeates all of space. Discovered in 1965 by Arno Penzias and Robert Wilson, this radiation has been a cornerstone in cosmological studies. Think of it as the leftover heat from the universe's explosive birth. This heat has traveled through space for over 13 billion years, providing us with a direct link to the past. This radiation was emitted when the universe was much hotter and denser, just a few 100,000 years after the Big Bang. At that time, the universe was a seething, opaque plasma of particles. As the universe expanded and cooled, this radiation stretched and cooled down to microwaves, which we can detect today using specialized telescopes. These telescopes have allowed us to map the CMB with incredible precision. The CMB provides a snapshot of the early universe, confirming several predictions of the Big Bang theory. It shows tiny temperature fluctuations that correspond to the seeds of galaxies and clusters we see today, offering a window into the universe's formative years. Section 6. The Fate of the Universe, Expanding Forever. If the universe began with a bang, how will it end? This question has fascinated scientists and philosophers for centuries. Will it continue expanding forever, or will it eventually collapse back on itself? The answer lies in understanding the forces at play in the cosmos. Cosmologists have proposed several possible scenarios for the fate of the universe, each with profound implications. These scenarios depend on the density of matter and the mysterious dark energy that permeates space. One possibility is that the universe will continue expanding forever, gradually cooling down and becoming a vast, dark, and empty place. This scenario is known as the Big Freeze. In the Big Freeze, stars will burn out, galaxies will drift apart, and the universe will become a cold, desolate expanse. Another possibility is the Big Crunch. In this scenario, the gravitational pull of all the matter in the universe will eventually halt the expansion and cause it to contract. Over billions of years, the universe will get smaller and denser, eventually collapsing back into a singularity, much like the one from which it originated. This dramatic collapse could lead to intense heat and pressure. This collapse could potentially lead to another Big Bang, creating a cyclical model of the universe. In this model, the universe would go through endless cycles of expansion and contraction. Whether the universe will freeze, crunch, or follow another path entirely remains one of the greatest mysteries of modern cosmology. The quest to understand our universe's ultimate fate continues to drive scientific discovery and exploration. Section 7. Beyond the Big Bang: Alternative Theories and Multiverse. While the Big Bang theory is the leading explanation for the origin of our universe, it is not the only one. Scientists are constantly exploring alternative theories and refining their understanding of the cosmos. Some theories propose that the Big Bang was not the beginning of everything but rather a transition from a previous state of existence. This leads to fascinating concepts like the Big Bounce, where the universe undergoes cycles of expansion and contraction. Another mind-boggling concept is the multiverse, which suggests that our universe is just one of many universes coexisting alongside each other. These universes might have different physical laws and constants, leading to an unfathomable diversity of cosmic landscapes. While the multiverse remains a highly speculative idea, it highlights the vastness of the unknown and the limits of our current understanding. Section 8. The Big Bang in a nutshell. So what have we learned about the Big Bang? This theory, supported by a wealth of observational evidence, describes the universe's beginning from an incredibly hot, dense state. It explains how space itself expanded and cooled, leading to the formation of elementary particles, stars, galaxies, and ultimately, us. The cosmic microwave background radiation provides a tangible echo of this momentous event. While the future of our universe remains uncertain, the possibilities, ranging from eternal expansion to a fiery collapse or even a cyclical rebirth, are both awe-inspiring and humbling. The Big Bang theory is a testament to the power of scientific inquiry and our ability to unravel the mysteries of the cosmos. Section 9. A Universe of Wonder. As we continue to explore the universe and delve deeper into its mysteries, The Big Bang Theory serves as a reminder of the incredible journey that led to our existence. It ignites our curiosity and encourages us to ask profound questions. What happened before the Big Bang? Are there other universes out there? What wonders await us in the vast expanse of the cosmos? The quest to understand our universe is a journey filled with wonder, and the Big Bang is a magnificent starting point.